Hello students, once we have developed the consumer problem, now we're going to talk about the producer problem, that in this case it's the developer. So for the developer, what we have is a production function given by Q. What they produce is housing floor space, and it's written as H depending on N and I, where Q is the floor space contained in a building, N is the amount of building materials including labor, wood, cement, steel, glass, everything. Sometimes in urban economics, for convenience, they call this capital. And L will be the land. Okay, and H will be the production function. So what we're going to assume about this function is that it observes diminishing marginal product of capital. When land is fixed, having extra doses of building material leads to smaller increases in floor space. Let me give you an example. So let's suppose we have a fixed amount of land, this little space, and when we increase in the amount of materials, then it will make the building taller. But with the land input fixed, extra doses of building material leads to smaller and smaller increases in floor space. You can think about it like if you need a taller building, you might need a stronger foundation which requires more material or thicker beams or space for elevators. So that's one characteristic of this production function. The other one is scale economies. In this case, if you double the input, you will have another exact same building. So housing production exhibits more or less constant returns to scale. Another assumption that Edward Glaser mentions in the video that you have to watch in perusal is that the buildings cover completely the land area and there's no open space around it. And the reason is that consumers value only floor space. So any land devoted to gardens would be wasted. It's not very realistic, but it makes the job. So economists claim that this is similar to Manhattan or Paris or Singapore, but you could allow garden space to be valued by consumers. The only problem is that the equations would be a little bit more complex. So let's suppose this is the revenue earned by the developer. It will be given by the price per square foot times the square footage that the developer produced. Now, to match the rental logic, both inputs are viewed as rented, so land rent per acre will be the relevant input price. And it's denoted by R. The rental rate per unit of building materials will be equal to I. Let's put this in a function. So this is the I, the price of this material, and this is the R, the price of this land. So the rental rate per unit of building material, sometimes it's constant, but the price of the building material is independent of where the structure is built. The material can be delivered anywhere in the city, no matter what. That's why it's constant. Then we need that R varies to make developers be willing to produce housing throughout the city. The reason is that locations closer to the center have higher price, so the developer has an incentive to produce there. Right? Then location far away from the core, well, they have a lower price and the developer doesn't want to produce there that much. So we need for these to be fixed. And the variable that helps is R. So this is more or less the city that we're thinking about. It's a city with skyscrapers in the center, and then as you move further away, you find shorter buildings. We're going to think that the city is a circle and the core is in the middle. This was even in the consumer problem. And what we're going to imagine is that this is full of housing all over the place, full with no space for anything else, okay? Okay, so I is fixed, therefore R has to do the work to equalize profits along the distance. And for that reason, there's an inverse relationship between R and distance, very similar to the consumer side. Now, if you compare this with an outside market, like the agricultural market, then it must be the case that in equilibrium, the rent is similar Otherwise, developers would rather go and develop elsewhere outside of the city, right? But well, as it happens with the consumer, the compensation differential of R can be viewed like a demand-based idea. So developers compete for land in the central location because floor space pays a high price there. And this competition beats land rents up near the center. And since there's little demand in the suburbs, then this leads to lower demand, lower rent in the suburbs. Competition for this land among developers will beat rent until profit is gone. In other words, the uniform profit that it's achieved all over the city, compensating for land rent differentials, will get developers to the point where they have zero profits. And this way, the model predicts one of the regularities of skyline: declining land rent and thus land value as distance to the center increases. When you want to buy an acre of land far away from the core, it's cheaper than closer to the core. This pattern also generates another regularity that it's related to building height. When the price of capital is fixed, that I that we talked about, and rent is rising as we are closer to the center, then the land input becomes more expensive relative to the capital input. So producers will shift their input mix in response. If land is more expensive compared to capital, developers will use more capital, building in a small square of land. This means that developers are building taller buildings, little land, but more capital, more material. Conversely, as land gets cheaper, moving towards the suburbs, the developers will use it more lavishly, constructing shorter buildings with more land and building gardens inside and so on and so forth. So overall, building height decreases as we are further from the center. And we can show this pattern in the next graph. Okay, in this graph, we find that these two developers are minimizing. The capital will be the vertical axis and the land will be the x-axis. The isoquant is this circular black line. And this shows all the capital land combinations that give you a floor space. In the text, they say 150,000 square feet. So here, with this combination of land and capital, you can produce 150,000 square feet, but also here and here and here, and even here, okay? So consider first the case of this developer close to the city core. This developer has a distance of x0 and a rent of x0, okay? The ISO cost line, it's given by this red line, and it has a slope of minus R0 divided by I. This is steep because R is high. This I is the same as this I. It doesn't change, but what changes is the R. So this R is bigger, R0 is high. So this slope is steep. To produce 150,000 square feet as cheaply as possible, the developer will buy the lowest possible ISO cost line, and therefore a little land and more capital would go a longer way. Now, in contrast, there's another developer away from the core, and he also wants to build 150,000 square feet. But here, distance is greater and R is smaller. So he faces a flatter ISO cost line. This R is smaller than R1 is smaller than R0. So his cost minimizing input bundle is L1N1. This has less capital and more land than the central city building. So this developer is building one-story complex. So this would be the difference between them both. Here we have, this is the capital at N0, This is the land at L0. And of course, in the blue case, when they are further away, L1 is given by this level, so it's more land, and it will use a lower amount of capital. Okay. Now the building heights are reflected in the amount of capital per acre of land given by a ratio. Let's divide N0 by L0 and then N1 by L1. Okay, let's put this race right here. So these ratios, L0 divided by N0, it's equal to the slope of the red dotted line. This ray is steeper than the blue ray. The building X0 is taller than the building at X1 because it has more materials in the same amount of land, more materials in little land. This means that it's a tall building. On the other hand, this slope of L1 divided by N1 shows that it has less materials but in a bigger amount of land. So it must be the case that this is a one-story building or, well, a short building. And therefore, the building height will fall as we move away from the core. Overall, from the producer problem, we get two predictions. As distance increases, the land rent decreases. And as distance increases, the height of the buildings will decrease as well.